Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here isn't just about stars, it's about the stories they hold, the quiet mysteries of direction and scale, and the gentle questions that help us find our place. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. Picture yourself standing outside on a clear night, looking up at the stars. The question comes naturally. What is above me? You see the sky stretching endlessly, constellations scattered like salt on black velvet, the soft band of the Milky Way arcing overhead. But then, the question deepens. Not just what is above your head on Earth, but what lies above the entire solar system. And if there is an above, there must also be a below. What lies beneath our cosmic neighborhood, in the opposite direction, hidden from view? The question sounds simple, almost childlike. Above and below are words we use every day, tied to the pull of gravity, to floors and ceilings, to the clear sense of up and down that our bodies understand instinctively. But in space, these words lose their certainty. There is no universal up, there is no absolute down. The cosmos does not come with directions printed on it like a map. And yet, the question remains, what is above our solar system, and what is below it? To answer, we must first accept something strange. In space, above and below are not truths but choices. They are frameworks we create, reference points we agree upon, so we can talk about direction in a place where direction is always relative. Astronomers have made this choice. They use the plane of the solar system, the flat disk traced by the orbits of planets, as a baseline. From that plane, they define north and south. North becomes above, south becomes below. It is arbitrary, yes, but it gives us a way to navigate. Once we accept this framework, the question opens into layers of discovery. Above our solar system lies not emptiness but structure. The heliosphere, an invisible bubble blown by the sun's breath. The interstellar medium, thin clouds of gas and dust drifting between stars. The halo of the Milky Way, a spherical region filled with ancient stars and dark matter. The galactic poles, windows through which we can see distant galaxies without the interference of our own. Each layer reveals something new, something unexpected. Below our solar system, the same layers mirror back. The heliosphere extends in all directions. The interstellar medium stretches beneath as well as above. The Oort cloud, a vast shell of icy comets, wraps the solar system not just overhead but underfoot, enclosing us in a sphere of frozen remnants from the birth of our system. The halo extends downward just as it rises upward. The structures are symmetrical, balanced, surrounding us on every side. But here is where the question becomes impossible in the most wonderful way. The solar system is not sitting still. It is moving, orbiting the center of the Milky Way at hundreds of kilometers per second. As it moves, it bobs gently above and below the galactic plane, like a bead on a string that oscillates as it circles. This means that what is above us now was beside us millions of years ago and will be below us millions of years from now. The directions shift over time. The structures remain, but our relationship to them changes. And there is more. The Milky Way itself is not flat. Its disk is warped, bent upward on one side and downward on the other, like a record that has been left too long in the sun. Above and below in this context are not neat dividing lines, but curves, tilts, and gentle arcs. The galaxy does not cooperate with our need for simplicity. It is vast, dynamic, and endlessly complex. To ask what lies above and below is to step into this complexity, to embrace it, to follow it wherever it leads. The impossibility of the question is not a barrier. It is an invitation. It invites us to think beyond the familiar, to stretch our minds across distances that dwarf anything we know on Earth. It invites us to see that even though space has no floor and no ceiling, we can still map it, explore it, understand it. The question may be impossible in a literal sense, but it is answerable in a human sense. We can describe what lies in these directions. We can trace the structures. We can tell the story. And so, as you settle into this journey, let the question work its way into your thoughts. What is above our solar system? What is below it? The answer is not a single thing, but a cascade of discoveries, each one leading to the next. It is layers of protection and exposure, of ancient history and ongoing motion, of visible stars and invisible matter. It is a story of scale, of perspective, of how we find our place in the vastness. Tonight, we will follow that story. We will lift our gaze above the plane of the solar system and peer down below it. We will trace the boundaries of the sun's influence and step beyond them. We will look through windows in the galaxy and see what lies farther still. We will encounter clouds and streams, halos and shells, visitors and remnants. We will ask what it means to speak of direction in a place where direction is chosen. And through it all, we will hold on to the thread of the question, letting it guide us gently into the unknown. The impossible question is the best kind of question. It does not have a single answer, but it has countless discoveries waiting along the way. Above and below our solar system lie wonders we are only beginning to understand. And the journey to see them starts here, now, with a simple act of curiosity. What is above? What is below? Let's find out together. Before we can explore what lies above and below, we need to know where we are. The solar system is not a fixed point in space. It is a moving system, orbiting the center of the Milky Way, carrying us along a path that takes hundreds of millions of years to complete. To understand what surrounds us, we must first create a map, a framework that gives us bearings in a place where there are no natural landmarks. The foundation of this map is the plane of the solar system. If you imagine the orbits of the planets, you can picture them as roughly circular paths around the Sun. Most of these orbits lie close to the same flat sheet of space, a disk-like structure that astronomers call the ecliptic plane. Earth's orbit defines this plane most precisely. From this baseline, we can extend lines perpendicular to it, one pointing north, the other pointing south. These directions give us our first sense of above and below. The ecliptic plane is not just a convenient abstraction, it is a reflection of how the solar system formed. Billions of years ago, a cloud of gas and dust collapsed under its own gravity, spinning as it contracted. That spin flattened the cloud into a disk, and from that disk, the sun and planets were born. The orbits of the planets still follow this ancient pattern. They remember the spin of the original cloud, tracing paths that lie within a few degrees of one another. The ecliptic is the fossil of that spinning disk, frozen into the geometry of our system. But the ecliptic is only the beginning. The solar system itself is tilted relative to the Milky Way. The plane of the galaxy, the flat disk of stars and gas that forms the main body of the Milky Way, does not align with the ecliptic. Instead, it is tilted by about 60 degrees. This means that when we talk about above and below in solar system terms, we are not necessarily talking about above and below in galactic terms. The two maps overlap but do not match. It is like holding two transparencies at an angle, each with its own grid, neither perfectly aligned. To navigate this complexity, astronomers use two coordinate systems. The ecliptic system is tied to Earth's orbit, useful for tracking planets and objects within the solar system. The galactic system is tied to the plane of the Milky Way, useful for understanding our position within the galaxy. Both systems have their poles, their north and south, their above and below. When we ask what lies above our solar system, we are often shifting between these frameworks, moving from one map to the other as the scale changes. The galactic plane is where most of the Milky Way's stars, gas, and dust reside. It is the crowded band of light we see stretching across the night sky, the luminous river that gives the galaxy its name. When we look along this plane, our view is dense with matter. Stars cluster thickly, dust clouds obscure the background. The line of sight is cluttered, rich, but difficult to penetrate. This is why looking perpendicular to the plane, looking above or below, is so valuable. It offers clearer views, windows through which we can see farther. The North Galactic Pole is the direction that points straight up out of the disk. It lies in the constellation Coma Berenices, a faint region of sky that does not immediately stand out. Yet this direction is one of the most important in astronomy. When we look toward the North Galactic Pole, we are looking away from the crowded plane into a region where the density of stars drops. This gives us an unobstructed view of distant galaxies, of the cosmic microwave background, of the large-scale structure of the universe. Above us, in this sense, is a window. The South Galactic Pole points in the opposite direction, straight down through the disk. It lies in the constellation Sculptor, another faint region, but equally significant. Looking toward the South Galactic Pole offers the same advantage as looking north. The dust and gas of the galactic plane are largely absent. The view is clearer. Surveys of the universe often focus on these two directions because they provide the cleanest paths out of the Milky Way. Below us, like above us, is a window into the cosmos beyond. But the map is not static. The solar system is moving. It orbits the galactic center at a speed of roughly 828,000 kilometers per hour, fast enough to circle the galaxy in about 225 million years. This orbital motion is steady, but it is not the only motion. The solar system also oscillates, bobbing gently above and below the galactic plane as it orbits. Over tens of millions of years, we drift upward, then downward, then back again. This means that our relationship to the plane changes over time. What is above us now will not always be above us. The oscillation is caused by the gravity of the galactic disk. As the solar system passes through the plane, it is pulled back toward it, like a weight on a spring. This creates a gentle wave, a slow bobbing motion that adds texture to our path through the galaxy. Above and below, in this context, are not fixed but shifting. The map we create is only a snapshot of our current position. Over geological time, the map changes and the structures we see from above or below shift with it. Distance also shapes the map. Close to the solar system, within a few light years, the structures are dominated by the heliosphere and the local interstellar medium. Farther out, tens of thousands of astronomical units away, the Oort cloud defines the boundary. Farther still, thousands of light years above and below, the galactic halo stretches. Each layer requires a different scale, a different way of thinking about space. The map we are creating is not flat but layered, nested like shells, each one enclosing the others. The invisible nature of much of this map adds to the challenge. We cannot see the heliosphere. We cannot see dark matter. We cannot see most of the interstellar medium with our eyes. The map must be built from indirect evidence, from measurements of particles and radiation, from the motions of stars and the bending of light. It is a map of the invisible, drawn with tools that extend our senses far beyond what biology provides. And yet, for all its complexity, the map works. It gives us a way to talk about direction, to organize our thinking, to explore the unknown, by defining the ecliptic plane and the galactic plane, by marking the poles and tracing the layers. we create a framework that turns the vastness of space into something navigable. Above and below become meaningful, not because the universe provides them, but because we choose them. The map is our creation, and it allows us to see. So, as we step forward into the layers above and below, remember that we are walking through a map we have drawn ourselves. The structures are real, the distances are real, but the directions are chosen, and that choice is what makes the journey possible. The first structure we encounter, the first layer above and below our solar system, is invisible to the eye but essential to our existence. It is called the Heliosphere, and it is the breath of the sun made manifest in space. The sun is not a quiet ball of light. It is constantly releasing a stream of charged particles, protons and electrons, hurled outward by the heat and pressure of its outer atmosphere. This stream is the solar wind, and it flows in all directions, filling a vast bubble around the solar system. The heliosphere is this bubble. It is the region of space where the solar wind still has influence, where the sun's particles are still moving outward, pushing against the thin gas of the interstellar medium. The boundary of the heliosphere, the edge where the solar wind meets resistance, is called the heliopause. Beyond that boundary, the influence of the sun fades, and the influence of the galaxy takes over. The heliosphere, then, is the cocoon that wraps our solar system, the shield that protects us from the full force of interstellar space. To understand the heliosphere, we must picture the sun as active, dynamic, always exhaling. Every second, millions of tons of particles stream outward from the sun's corona, the superheated outer layer of its atmosphere. These particles are so energetic that they escape the sun's gravity entirely, racing away at speeds of hundreds of kilometers per second. They carry with them the sun's magnetic field, stretching it out into space, twisting it into spirals as the sun rotates. This extended magnetic field is part of the heliosphere, shaping the flow of particles and influencing the environment around us. The heliosphere is vast. From the sun to the heliopause is roughly 18 billion kilometers, depending on the direction and the strength of the solar wind at any given time. To put that in perspective, the distance from the sun to Earth is about 150 million kilometers. The heliosphere extends more than 100 times farther. It is so large that light itself takes over 16 hours to cross from the sun to its edge. Above us and below us, this bubble stretches, wrapping the entire solar system in the sun's influence. The shape of the heliosphere is not perfectly spherical. Because the solar system is moving through the galaxy, the heliosphere is compressed in the direction of motion and stretched out behind. It resembles a comet, with a rounded nose facing the direction we are travelling and a long tail trailing behind. This asymmetry is caused by the pressure of the interstellar medium. Where the solar wind pushes against oncoming gas, it compresses. Where it flows into relatively empty space, it expands. Above and below, the shape varies, reflecting the balance of forces. The discovery of the heliosphere's structure came from spacecraft. In the 1970s, 2 Voyager probes were launched, sent to explore the outer planets and then continue into interstellar space. For decades, they travelled outward, passing Jupiter, Saturn, Uranus, and Neptune, then heading toward the edge of the known solar system. In 2012, Voyager 1 crossed the heliopause, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. The data they sent back confirmed the existence of the boundary and revealed details about its structure. What the Voyagers found was a transition, not a wall. As they approached the heliopause, the solar wind slowed and became turbulent. Particles from the interstellar medium began to appear, mixing with the solar wind. The magnetic field shifted, no longer dominated by the sun. Then, beyond the boundary, the solar wind disappeared entirely, replaced by the thin gas of the galaxy. The heliopause was real, measurable, a clear edge to the sun's influence. Above and below, the same boundary exists, marking the limit of the heliosphere. The heliosphere serves a critical function. It acts as a shield against galactic cosmic rays, high-energy particles that stream through the galaxy, born from supernovae and other violent events. These particles are dangerous. They can damage DNA, disrupt electronics, and strip away atmospheres. Without the heliosphere, Earth would be exposed to far more radiation. The magnetic field of Earth provides a second layer of defense, but the heliosphere is the first line. It deflects and slows many of the cosmic rays, reducing their intensity before they reach the inner solar system. Above and below, the heliosphere extends equally, though the details of its shape may vary. The protection it offers is not uniform. Cosmic rays can still penetrate, especially during periods when the solar wind is weak. But overall, the heliosphere reduces the radiation environment significantly. This shielding may be one of the reasons life has flourished on Earth. Planets without such protection, orbiting, stars with weaker winds or no winds at all, might face harsher conditions. The heliosphere also changes over time. The Sun goes through cycles of activity, roughly 11 years long. During active periods, the solar wind strengthens, pushing the heliopause outward. During quiet periods, the wind weakens, and the heliopause contracts. This breathing in and out means that the boundary above and below us is not fixed. It moves, sometimes by billions of kilometers, responding to the rhythm of the sun. The cocoon expands and contracts, always present but never static. The discovery of the heliosphere reshaped our understanding of the solar system. Before the Voyagers, the edge of the solar system was thought to be somewhere near the orbit of Pluto. Now, we know it extends much farther. The heliosphere is part of the solar system in a very real sense, even though it contains no planets or moons. It is defined by the sun's influence, and that influence reaches far, above and below. The heliosphere is the first layer of structure, the first answer to the question of what surrounds us. And so, as we imagine the space above and below our solar system, we begin with this invisible bubble, the heliosphere, the breath of the sun flowing outward in all directions. It is the cocoon we live inside, the shield that protects us, the boundary that separates our local neighborhood from the galaxy beyond. It is vast, dynamic, and essential, and it is the first step in understanding what lies farther out. When the Voyager spacecraft crossed the heliopause, they did not encounter a wall. There was no dramatic shift, no sudden blackness, no moment when everything changed at once. Instead, the transition was gradual, a slow fading of one environment and the emergence of another. The solar wind, which had been rushing outward for decades of the spacecraft's journey, began to thin. Particles from outside, from the interstellar medium, started to appear in the detectors. The magnetic field shifted orientation, no longer tied to the sun's rotation but aligned with the galaxy's own fields. It was a crossing, yes, but a gentle one. This was humanity's first response to the question of what lies beyond the bubble. We sent emissaries, mechanical explorers, carrying instruments sensitive enough to measure the change. And they told us that beyond the heliosphere lies something different but not alien. The interstellar medium is not a void, it is not a wall. It is a continuation of space, filled with gas and dust and radiation, but thinner, calmer, and shaped by forces larger than a single star. Above and below, beyond the heliopause, this medium stretches, and the Voyagers were the first to touch it directly. The data they sent back revealed details that had been guessed at but not confirmed. The density of particles changed. Inside the heliosphere, the solar wind dominates, with densities of a few particles per cubic centimetre. Outside, in the interstellar medium, the density is lower but not negligible. A few atoms per cubic centimetre, mostly hydrogen and helium, drifting between the stars. It sounds like emptiness, but over the vast distances of space, even such thin matter accumulates. It absorbs light, scatters radiation, and interacts with magnetic fields. It is sparse, but it is real. The temperature also shifted, though in a counterintuitive way. Inside the heliosphere, the solar wind is hot, in terms of particle energy. Outside, the interstellar medium is even hotter, with particles moving at higher average speeds. But because the density is so low, this heat does not feel warm in the way we know on Earth. There is not enough matter to transfer heat effectively. It is a strange kind of hot, defined by energy rather than sensation. Above and below, the interstellar medium exists in this state, a thin plasma filling the space between stars. The magnetic field beyond the heliopause was another discovery. Inside the heliosphere, the Sun's magnetic field dominates, spiraling outward with the solar wind. Outside, the field is galactic in origin, shaped by the rotation of the Milky Way and the motions of gas and plasma on larger scales. The Voyagers measured this field, confirming that it runs parallel to the galactic plane in the region of space near the solar system. This means that above and below, the magnetic field wraps around the heliosphere, guiding charged particles and shaping the flow of cosmic rays. Cosmic rays themselves change in intensity beyond the heliopause. Inside the heliosphere, many are blocked or deflected by the solar wind and the Sun's magnetic field. Outside, their flux increases. The Voyagers detected this rise, confirming that the heliosphere is indeed a shield. But they also found that the increase is not uniform. Some cosmic rays come from all directions. Others seem to follow the magnetic field lines, streaming along preferred paths. Above and below, the environment beyond the bubble is filled with these high-energy travelers, particles accelerated by distant supernovae and other violent events. The crossing of the heliopause also revealed something about the local interstellar medium. The solar system is currently passing through a region called the local interstellar cloud, a relatively warm and diffuse cloud of gas about 30 light-years across. This cloud is part of a larger structure, the local bubble, a cavity carved out by ancient supernovae. The heliosphere sits within this cloud, and the properties of the cloud influence the shape and size of the heliosphere. Above and below, the cloud surrounds us, shaping the boundary of the bubble. The first response to crossing the bubble was also emotional. For scientists and engineers who had worked on the Voyager mission for decades, the moment was profound. The spacecraft, launched in the 1970s, had travelled farther than any human-made object. They had left the domain of the Sun and entered the domain of the galaxy. It was a milestone, a step beyond, a confirmation that exploration is possible even at such distances. Above and below, the Voyagers continue to travel, their signals growing fainter but still reaching Earth, still sending back data from the interstellar medium. But the first response also brought new questions. What lies farther beyond? How does the interstellar medium change as we move away from the solar system? Are there other structures, other boundaries, other transitions waiting to be discovered? The Voyagers will continue outward for decades, perhaps centuries, until their power finally runs out. But even then, they will drift, silent messengers carrying information about humanity into the galaxy. Above and below, they are the first explorers of the space beyond the bubble. The crossing also highlighted the dynamic nature of the heliopause. The boundary is not fixed. It responds to changes in the solar wind, to variations in the pressure of the interstellar medium, to the motion of the solar system through the galaxy. Sometimes the heliopause is closer. Sometimes it is farther. The Voyagers crossed at a particular moment in time, at a particular location. Above and below, the boundary may be different, shaped by local conditions. The first response taught us that the edge of the solar system is not a line on a map, but a living, shifting interface. And so, the first response to the question of what lies beyond the bubble is this: another environment, thinner but not empty, shaped by the galaxy rather than the sun, filled with particles and fields and radiation. It is the interstellar medium, the space between stars, and the Voyagers have given us our first direct taste of it. Above and below, the medium stretches, waiting for future explorers to venture even farther, to see what else lies in the quiet expanse beyond the sun's breath. Space, by its very name, suggests emptiness. When we think of the vacuum between stars, we imagine nothing, a blank canvas, a void. And in many ways, this is accurate. The interstellar medium is far emptier than any vacuum we can create on Earth. A cubic centimetre of the best laboratory vacuum might still contain millions of molecules. A cubic centimetre of interstellar space contains perhaps a handful of atoms. By earthly standards, it is as close to nothing as matter can be. And yet, it is not nothing. This is the contradiction. Space is empty, yet it is full. The interstellar medium, the thin gas and dust that fills the space above and below our solar system, is made mostly of hydrogen and helium, the simplest and most abundant elements in the universe. These atoms drift through space, spread so thinly that encounters between them are rare. In some regions, the density is only a fraction of an atom per cubic centimetre. In others, denser clouds, it might reach thousands of atoms per cubic centimetre. But even the densest clouds are far emptier than air. The contradiction is one of scale. What seems empty up close is full when seen across light years. Dust is part of this fullness. Tiny grains, smaller than a micron, made of silicates, carbon compounds, and ices, float through the interstellar medium. They are sparse, but not negligible. When starlight passes through regions rich in dust, it is dimmed and reddened, a process called interstellar extinction. This is why some parts of the Milky Way appear dark, cut through with lanes of shadow. The darkness is not absence, it is dust, blocking the light of stars behind it. Above and below, dust is scattered, part of the contradiction of empty space that obscures. Magnetic fields also thread through the interstellar medium, invisible but present. They are weak compared to the fields we know on Earth, but across vast distances they guide the motion of charged particles, shape the structure of clouds, and influence the birth of stars. Astronomers can detect these fields by observing the polarization of starlight, or the emission of radio waves from particles spiraling along field lines. Above and below, the fields weave through space, adding another layer to the fullness of the void. Cosmic rays are another part of the contradiction. These high-energy particles, mostly protons and atomic nuclei, stream through the galaxy at nearly the speed of light. They are born in violent events, supernova explosions, pulsar winds, the regions near black holes. Once accelerated, they travel vast distances, scattering off magnetic fields, changing direction, but rarely stopping. The interstellar medium is filled with them. Every second, your body is struck by a few, though at Earth's surface they are mostly secondary particles created when cosmic rays hit the atmosphere. Above and below, cosmic rays flow constantly, invisible travellers that fill the emptiness. Radiation of all kinds permeates the space between stars. Starlight, of course, the photons streaming outward from billions of suns, but also infrared radiation from warm dust, ultraviolet light from hot young stars, X-rays from supernova remnants, radio waves from pulsars, and from the ionized gas itself. The interstellar medium glows faintly, in wavelengths we cannot see with our eyes, but can detect with instruments. Above and below, this glow fills the space, a background hum of energy that never stops. The contradiction deepens when we consider that even in the emptiest regions, space is never truly still. Gas drifts, driven by the pressure of starlight, by the shock waves from exploding stars, by the gravitational pull of galaxies. Clouds collide, merge, fragment. Stars are born from these clouds, gathering matter into dense cores that eventually ignite. When stars die, they return material to the medium, enriching it with heavy elements. The interstellar medium is not static. It is cycling, flowing, transforming, empty, yet full of motion. Above and below the solar system, the local interstellar medium has its own character. The solar system is currently passing through the local interstellar cloud, a region about 30 light-years across, warmer and less dense than some other clouds. This cloud is part of a larger cavity, the local bubble, carved out by supernovae over the past 10 to 20 million years. The bubble is a region of low-density gas, but even here, the contradiction holds. Low density does not mean empty. It means thinner, but still present. Above and below, the local bubble stretches, and within it, we drift. The emptiness of space also depends on what you are looking for. If you are looking for air, for pressure, for substance you can feel, then space is empty. But if you are looking for atoms, for particles, for fields and radiation, then space is full. The contradiction is a matter of perspective. On Earth, we are surrounded by matter so dense that we take it for granted. In space, matter is so sparse that it seems absent. But it is there, always there, shaping the environment in ways both subtle and profound. The interstellar medium also plays a role in the life of the galaxy. It is the reservoir from which stars are born. When a cloud of gas becomes dense enough, gravity takes over, pulling it into clumps that eventually ignite as stars. These stars then shape the medium around them, heating it with radiation, blowing it outward with stellar winds, enriching it with heavy elements when they explode. The cycle continues. Stars born from the medium, stars returning to it. Above and below, this cycle is ongoing, filling the emptiness with the raw material of creation. The contradiction also touches on the nature of vacuum itself. In quantum mechanics, even empty space is not truly empty. Virtual particles appear and disappear, borrowing energy from the vacuum for fleeting moments. These fluctuations are real, measurable, and they contribute to phenomena we observe, such as the Casimir effect. The interstellar medium, sparse as it is, sits atop this quantum foam, adding a few real particles to the sea of virtual ones. Above and below, the emptiness is layered, full in ways we are only beginning to understand. And so, the contradiction stands. Space is empty, yet it is full. The interstellar medium is sparse, yet it shapes everything. Above and below our solar system, the void is not void at all. It is gas and dust, fields and radiation, particles and waves, all spread so thinly that they seem like nothing but present nonetheless. The contradiction is not a flaw in our thinking. It is the truth of the cosmos, a reminder that fullness and emptiness are not opposites but perspectives, scales, ways of seeing the same reality. When we ask what lies above and below the solar system, one of the most important answers involves direction. Not the direction of objects within our immediate neighbourhood, but the direction that takes us straight out of the crowded disk of the Milky Way and into clearer space. These directions are defined by the galactic poles, the north and south points perpendicular to the plane of the galaxy. They are not places, but orientations, lines of sight that offer some of the best views of the universe beyond our own galaxy. The galactic coordinate system is designed to map the Milky Way. Just as Earth has a north and south pole defined by its rotation, the galaxy has poles defined by the orientation of its disk. The North Galactic Pole is the direction that points straight up out of the disk, away from the crowded plain of stars and gas. It lies in the constellation Coma Berenices, a faint patch of sky that does not immediately stand out to the naked eye. But to astronomers, this direction is invaluable. Looking toward the North Galactic Pole means looking through the thinnest part of the galaxy, where the density of stars drops and the view opens outward. The South Galactic Pole points in the opposite direction, straight down through the disk. It lies in the constellation Sculptor, another faint region, equally important. Looking toward the South Galactic Pole offers the same advantage. The dust and gas that obscure our view along the galactic plane are largely absent in this direction. The line of sight is clearer, less cluttered, more transparent. Surveys of distant galaxies, of the cosmic microwave background, of the large-scale structure of the universe, often focus on these two directions because they provide the cleanest windows out of the Milky Way. Above and below, in the context of the galactic poles, refer to these perpendicular directions. Above means toward the North Galactic Pole. Below means toward the South Galactic Pole. When we talk about what lies above our solar system, we are often talking about what lies in this direction, out of the disk, into the halo and beyond. The theories of galactic structure, of dark matter distribution, of the cosmic web, all depend on observations made through these windows. Peel us a view of the Coma cluster, one of the richest galaxy clusters in the nearby universe. This cluster lies more than 300 million light-years away, containing thousands of galaxies bound together by gravity. It is one of the great structures of the cosmos, and to look toward the North Galactic Pole is to look in its direction. Beyond the Coma cluster lie even more galaxies, stretching into the cosmic web, the large-scale structure that organizes the universe. Above us, the North Pole opens a path into this vastness. The South Galactic Pole offers a different but equally rich view. In this direction lies the Sculptor group, one of the nearest collections of galaxies outside our local group. This group includes spiral galaxies, dwarf galaxies, and irregular systems, each one a world unto itself. The Sculptor galaxy, also known as NGC 253, is one of the brightest in this group, a starburst galaxy where stars are forming at a rapid rate. To look below, toward the South Galactic Pole, is to see these nearby companions and the structures beyond them. The theories of what lies above and below the galactic disk also involve the halo of the Milky Way. The halo is a roughly spherical region surrounding the disk, filled with ancient stars, globular clusters, and dark matter. When we look toward the galactic poles, we are looking through this halo. The stars in the halo are older than those in the disk, metal poor and faint, remnants of the galaxy's earliest days. Globular clusters, dense balls of hundreds of thousands of stars, orbit through the halo in wide elliptical paths. Above and below, these clusters are scattered, marking the extent of the halo. Dark matter is thought to dominate the halo, outweighing visible matter by a factor of 5 or more. This unseen mass shapes the motions of stars and clusters, holds the galaxy together, and extends far beyond the visible disk. When we look toward the galactic poles, we are looking through regions where dark matter is present, though invisible. Theories of dark matter distribution predict that the halo is roughly spherical, surrounding the disk on all sides. Above and below, dark matter fills the space, shaping the structure we observe. The galactic poles also play a role in cosmology, the study of the universe as a whole. The cosmic microwave background, the faint afterglow of the Big Bang, is spread evenly across the sky. But observing it cleanly requires looking through regions where the Milky Way does not interfere. The galactic plane is filled with stars and dust that emit their own radiation, contaminating the signal. The galactic poles, by contrast, offer clearer paths. Above and below, the cosmic microwave background shines through more cleanly, allowing precise measurements of its temperature and fluctuations. These measurements have revealed the age of the universe, the distribution of matter and energy, and the seeds of structure that grew into galaxies and clusters. The theories of the Big Bang, of inflation, of dark energy, all depend on data gathered through the windows of the galactic poles. Above and below, these directions are not just about our local neighborhood, they are paths into the deepest history of the cosmos. The theories also recognize that the view from the galactic poles changes over time. The solar system orbits the galaxy, moving through different regions of the halo, different streams of stars, different densities of dark matter. What we see above us now may shift slightly as we continue our orbit. The structures remain, but our perspective changes. The galactic poles are fixed in the coordinate system, but our relationship to them is dynamic, evolving with the motion of the solar system. And so, when we think about what lies above and below our solar system, the galactic poles are a crucial part of the answer. They are the directions that take us out of the disk, through the halo, and into the universe beyond. They are the windows through which we see distant galaxies, ancient clusters, and the faint glow of the Big Bang. Above and below, the galactic poles define our view, shaping the theories we build and the discoveries we make. Surrounding the flat disk of the Milky Way is a structure far larger and more diffuse, a spherical region called the galactic halo. It is not as bright as the disk. It does not shine with the same intensity, but it is essential to the galaxy's structure, and it holds within it some of the oldest stars in existence. When we look above and below the solar system, one of the things we encounter is this halo, stretching far out into space, marking the boundary of the galaxy's influence. The halo is made of several components. The most visible are the stars, though even they are sparse compared to the crowded disk. These halo stars are old, metal-poor, meaning they contain very few elements heavier than hydrogen, helium. This chemical signature tells us they were born in the early days of the galaxy, before many generations of stars had lived and died, enriching the interstellar medium with heavy elements. Above and below, these ancient stars drift, moving in orbits that take them far from the galactic plane and back again. Globular clusters are another key part of the halo. These are dense, spherical collections of stars, each cluster containing tens of thousands to millions of stars packed into a relatively small volume. Globular clusters are among the oldest structures in the galaxy, with ages often exceeding 10 billion years. They orbit the Milky Way in wide, elliptical paths, spending much of their time in the halo. When we look above or below the disk, we can find these clusters shining faintly, distant beacons of ancient starlight. The investigation of the halo began with observations of these globular clusters. In the early 20th century, astronomer Harlow Shapley used them to determine the size and structure of the Milky Way. By mapping their positions, he realized they were distributed in a spherical pattern around the galaxy, not confined to the disk. This led to the understanding that the Milky Way has a halo, a spherical component surrounding the flat spiral. Above and below, the globular clusters mark the extent of this structure, tracing its shape. But the halo is not just stars and clusters. It is also filled with dark matter, the invisible mass that dominates the galaxy's gravity. While the stars and clusters are the visible parts of the halo, dark matter makes up the majority. It does not emit light, does not interact with radiation, but its gravitational pull shapes the motions of everything in the galaxy. Above and below, dark matter extends far beyond the visible halo, forming a vast, unseen structure that holds the Milky Way together. The investigation of dark matter in the halo comes from studying the motions of stars and gas. When, Astronomers measure how fast stars orbit the galaxy. They find that the speeds are too high for the visible matter alone. There must be additional mass, unseen mass, providing the extra gravity. This dark matter is thought to form a roughly spherical halo, extending hundreds of thousands of light years from the galactic center. Above and below, this halo is present, shaping the environment, even though we cannot see it directly. Streams of stars are another feature of the halo. These are the remnants of smaller galaxies that were consumed by the Milky Way over billions of years. As a smaller galaxy approaches the Milky Way, tidal forces pull it apart, stretching its stars into long, thin streams. These streams continue to orbit the galaxy, tracing the path of the original dwarf galaxy. Above and below, several such streams have been identified, arcing through the halo, evidence of the Milky Way's violent past. One of the most famous streams is the Sagittarius stream, the remnant of the Sagittarius dwarf elliptical galaxy. This dwarf galaxy is still in the process of being absorbed by the Milky Way, and its stars are spread out in a great loop around the galaxy. The stream can be detected by mapping the positions and velocities of stars in the halo. Above and below, the Sagittarius stream marks a trail of disruption, a fossilized record of a past encounter. The investigation also involves studying the chemical composition of halo stars. Because they are so old, their composition reflects the early conditions of the galaxy. By analyzing their light, astronomers can determine what elements they contain, how they formed, and when they were born. This information helps piece together the history of the Milky Way, revealing how it grew from smaller building blocks into the large spiral we see today. Above and below, each halo star carries part of this history. The halo also contains high-velocity clouds, large concentrations of gas moving at speeds different from the rotation of the disk. Some of these clouds may be material falling into the Milky Way from intergalactic space, while others may be remnants of dwarf galaxies or gas blown out of the disk by supernova explosions. Above and below, these clouds drift, adding to the complexity of the halo's structure. The investigation of the halo is ongoing. New surveys map more stars, trace more streams, and refine our understanding of dark matter. Each discovery adds detail to the picture. The halo is not a simple, uniform structure, but a complex, layered region shaped by billions of years of evolution. Above and below, it stretches, a spherical envelope surrounding the disk, holding the galaxy together, and carrying within it the echoes of its past. Tracing the halo also connects us to the larger universe. The Milky Way is not unique in having a halo. Other spiral galaxies have similar structures, and by studying our own halo, we learn how galaxies form and evolve in general. Above and below, the halo is a laboratory for understanding galactic dynamics, dark matter, and the processes that shape the cosmos. It is vast, faint, and often overlooked, but it is essential to the story of our galaxy. The halo of the Milky Way is not smooth or uniform. It is textured with streams, long arcs of stars that trace the orbits of smaller galaxies that once existed independently but were consumed by our own. These streams are the data, the evidence of the Milky Way's growth over billions of years. They are fossilized orbits, remnants of past encounters, and they tell a story of collision, absorption, and transformation. Above and below the disk, these streams weave through the halo, waiting to be read. The discovery of stellar streams required careful observation. Stars in the halo are faint and scattered, blending into the background unless large numbers of them are mapped. With the advent of digital surveys and sophisticated telescopes, astronomers began to notice patterns. In some regions, the density of stars was slightly higher than expected. In others, stars moved with similar velocities, as if they were part of a coherent group. These overdensities and kinematic patterns revealed the presence of streams. One of the first and most dramatic streams discovered is the Sagittarius stream. The Sagittarius dwarf elliptical galaxy is a small galaxy currently being torn apart by the Milky Way's gravity. As it orbits our galaxy, tidal forces stretch it, pulling stars away from its core and spreading them into a long trail. This trail wraps around the Milky Way in great loops above and below the disk, tracing the orbit of the original dwarf galaxy. The Sagittarius stream is visible in maps of halo stars, a faint ribbon of light marking the path of destruction. The data from the Sagittarius stream tell us several things. First, they confirm that the Milky Way has been consuming smaller galaxies for a long time. The stream is old, millions of years in the making, and it will continue to spread and fade as the dwarf galaxy is fully absorbed. Second, the stream's shape and position reveal the gravitational potential of the Milky Way. By modelling how the stream formed and evolved, astronomers can infer the distribution of dark matter in the halo. Above and below, the stream is a probe, a natural experiment that maps the unseen mass. Other streams have been found as well. The GD1 stream is thought to be the remnant of a globular cluster disrupted by the Milky Way's gravity. It is long and thin, stretching across the sky, visible only in detailed surveys of halo stars. The orphan stream is another, named because its parent system has not been identified. These streams and others like them are scattered through the halo, each one a piece of the puzzle, each one contributing data to our understanding of the galaxy's history. The streams also tell us about the merger history of the Milky Way. Our galaxy did not form in isolation. It grew by absorbing smaller systems, adding their stars, gas, and dark matter to its own. Each stream is the remnant of one of these mergers. By counting the streams, mapping their positions, and analyzing their properties, astronomers can reconstruct how many dwarf galaxies the Milky Way has consumed and when those mergers happened. Above and below, the streams are a timeline, a record written in stars. The data also reveal the complexity of tidal disruption. When a smaller galaxy approaches the Milky Way, it does not simply vanish. Gravity pulls it apart gradually, stripping stars from its outer layers first, then deeper layers, until only the core remains. The stripped stars do not scatter randomly. They follow the orbit of the original galaxy, forming a coherent stream. Over time, the stream spreads out, wrapping around the Milky Way multiple times. Above and below, these streams overlap, creating a complex web of stellar remnants. Mapping the streams requires careful analysis. Astronomers use large surveys like the Sloan Digital Sky Survey and the Gaia mission to measure the positions, brightnesses, and velocities of millions of stars. By analyzing this data, they can identify patterns that indicate the presence of streams. The work is painstaking, but it has revealed a halo far more structured than once thought. Above and below, the halo is not a simple cloud of stars, but a tapestry of streams, each one telling its own story. The streams also help us understand the nature of dark matter. If dark matter were distributed differently, the streams would have different shapes. By comparing observed streams with computer simulations, astronomers can test models of dark matter distribution. Some streams show gaps or irregularities, which might be caused by the gravitational pull of dark matter clumps. Above and below, the streams are sensitive probes, revealing details about the invisible halo. The chemical composition of stream stars adds another layer of data. Stars in different streams may have different abundances of heavy elements, reflecting the conditions in their parent galaxies. By measuring these abundances, astronomers can learn about the star formation histories of the dwarf galaxies that were absorbed. Some streams contain metal-poor stars, indicating they came from small, old systems. Others have more metals, suggesting more recent or more massive progenitors. Above and below, the streams carry chemical fingerprints, clues to their origins. The discovery of streams has also led to the identification of intact dwarf galaxies that are currently being disrupted. The Sagittarius dwarf is one example, but there are others. Some are so faint they were only discovered because their streams betrayed their presence. These ongoing disruptions allow astronomers to watch the process in real time, seeing how tidal forces work and how streams form. Above and below, the halo is not static but active, still being shaped by mergers. The data from streams also connect to the broader study of galaxy formation. All large galaxies likely grew by absorbing smaller ones. The streams in the Milky Way's halo are examples of a universal process. By studying them, we learn how galaxies like ours came to be. Above and below, the streams are local evidence of cosmic-scale processes, remnants that link our galaxy to the larger story of how structure formed in the universe. And so, the streams of the past are more than just faint arcs of stars. They are data, evidence, history. They tell us about mergers, about dark matter, about the growth of the Milky Way. Above and below, they weave through the halo, waiting to be mapped, analysed and understood. Each stream is a thread in the tapestry, and together they reveal the dynamic, violent and beautiful history of our galaxy. Among all the structures that fill the space above and below our solar system, none is more mysterious than dark matter. It is invisible. It does not emit light. It does not absorb light. It does not reflect light. And yet, it is there, everywhere, dominating the mass of the galaxy, shaping the motions of stars, holding the halo together. Dark matter is the deeper mystery, the unseen presence that reminds us how little we truly understand about the universe. When astronomers measure how fast stars orbit the Milky Way, they find something unexpected. Stars far from the galactic center move faster than they should, based on the visible matter alone. According to Newton's laws, stars farther out should orbit more slowly, just as planets farther from the Sun orbit more slowly. But in the Milky Way, the speeds remain roughly constant, even at great distances. This flat rotation curve can only be explained if there is additional mass, unseen mass, providing extra gravity. That unseen mass is dark matter. It is thought to form a vast halo surrounding the galaxy, extending far beyond the visible disk and stars. This dark matter halo is roughly spherical, reaching hundreds of thousands of light years from the galactic center. Above and below, it is present, contributing the majority of the galaxy's gravitational pull. Without it, the Milky Way would not hold together. Stars would fly off into space. The galaxy would disintegrate. Dark matter is the glue, the invisible framework that binds everything. But what is dark matter? No one knows. It is one of the great unsolved problems in physics. We know it exists because of its gravitational effects, but we do not know what it is made of. It could be particles that do not interact with light, such as weakly interacting massive particles, or WIMPs. It could be lighter particles, called axions. It could be something more exotic, perhaps a modification of gravity itself rather than actual matter. Experiments around the world are searching for dark matter particles, but so far, none have been detected directly. The mystery deepens when we consider how much dark matter there is. In the Milky Way, dark matter outweighs visible matter by about 5 to 1. The stars, gas, and dust we can see are only a small fraction of the total mass. The rest is dark. Above and below, the halo is filled with this invisible substance. It does not clump into planets or stars. It does not form disks. It simply fills the volume, a diffuse halo of unseen particles. Gravitational lensing provides indirect evidence of dark matter's presence. When light from a distant galaxy passes near a massive object, its path bends, much like light through a lens. By measuring this bending, astronomers can map the distribution of mass even if the mass is dark. Observations of galaxy clusters show halos of dark matter surrounding them, far more massive than the visible galaxies. Above and below, dark matter shapes the light we see, bending it, magnifying it, revealing its presence through distortion. The halo of dark matter is not perfectly smooth. Simulations suggest it may be clumpy, with dense regions and thin regions shaped by the history of mergers and the flow of matter. Some of these clumps may be remnants of smaller dark matter halos that were absorbed along with dwarf galaxies. Others may be structures that formed naturally as dark matter collapsed under its own gravity. Above and below, the dark matter halo may be textured, filled with substructure too faint to detect directly. Dark matter also plays a role in the formation of the galaxy. In the early universe, before stars existed, dark matter began to clump under its own gravity. These clumps attracted ordinary matter, gas that cooled and formed the first stars. Without dark matter, galaxies might never have formed. It is the scaffolding, the foundation on which visible structures are built. Above and below, dark matter was there first, shaping the environment into which stars and gas later fell. The streams of stars in the halo can be used to study dark matter. By modelling how streams form and evolve, astronomers can infer the distribution of dark matter. If the dark matter halo were distributed differently, the streams would have different shapes. Some streams show gaps or irregularities, which might be caused by dark matter clumps perturbing the orbits of stars. Above and below, the streams are probes, sensitive to the unseen mass around them. The mystery of dark matter extends beyond the Milky Way. Every galaxy seems to have a dark matter halo. Clusters of galaxies are dominated by dark matter. Even the large-scale structure of the universe, the cosmic web, is shaped by dark matter. It is the majority of the matter in the universe, yet we cannot touch it, see it, or identify it. Above and below, in every direction, dark matter fills the cosmos, a mystery we live within. Some scientists have proposed alternatives to dark matter, such as modified Newtonian dynamics, or MOND, which suggests that gravity behaves differently on large scales. These theories can explain some observations, but they struggle with others. Dark matter remains the leading explanation because it fits the widest range of data. Above and below, the evidence for dark matter is overwhelming, even if its nature remains hidden. The search for dark matter continues. Deep underground laboratories shield detectors from cosmic rays, waiting for the faintest signal of a dark matter particle colliding with an atom. Particle accelerators search for new particles that could be dark matter. Telescopes map the distribution of dark matter through gravitational lensing and galaxy dynamics. Above and below, the search is ongoing, driven by the hope that one day the mystery will be solved. And so, dark matter is the deeper mystery of the space above and below our solar system. It is everywhere, dominating the mass of the galaxy, shaping its structure, holding it together. Yet it remains invisible, elusive, unknown. It is a reminder that the universe is full of things we cannot see, forces we do not understand, mysteries that wait patiently for us to unravel. Above and below, dark matter lingers, silent and unseen, the greatest puzzle of the cosmos, far beyond the orbits of the planets. Farther still than the Kuiper belt with its scattered icy bodies, lies a structure so vast and so remote that it is more idea than observation. This is the Oort cloud, a spherical shell of comets thought to surround the solar system at immense distances. It is the turning point in our journey, the boundary between what is clearly part of the solar system and what begins to blend into interstellar space. Above and below, the Oort cloud stretches, a frozen halo marking the outermost reach of the Sun's gravitational influence. The Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. He noticed that long-period comets, those with orbits lasting thousands or millions of years, seemed to come from a vast reservoir far beyond the known planets. Their orbits were too elongated, too randomly oriented to be explained by the Kuiper belt or by interactions with the giant planets. Oort suggested that these comets originated in a great spherical shell surrounding the solar system, perturbed into the inner system by the gravity of passing stars or the tidal forces of the Milky Way. The distances involved are staggering. The inner edge of the Oort cloud is thought to begin around 2,000 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun. The outer edge may extend as far as 100,000 astronomical units, roughly halfway to the nearest star. Light from the Sun takes more than a year to reach the outer edge of the Oort cloud. Above and below, the cloud is so distant that it is almost in interstellar space, yet still bound to the Sun. The Oort cloud is divided into 2 regions. The inner Oort cloud, sometimes called the Hills cloud, is a denser, disk-like region closer to the ecliptic plane. The outer Oort cloud is more spherical, extending in all directions. Together, they form a shell that wraps the solar system like a cocoon. Above and below, the Oort cloud is present, not confined to a plane but surrounding us on every side. The objects in the Oort cloud are remnants from the early solar system. When the planets formed, countless smaller bodies were scattered by their gravity. Some were ejected entirely, cast out into interstellar space. Others were thrown into distant orbits, too far to return quickly but still bound to the Sun. Over billions of years, these scattered objects settled into the Oort cloud, forming the vast reservoir we hypothesize today. Above and below, they remain, drifting silently, frozen relics of the solar system's youth. We have never seen the Oort cloud directly. Its objects are too small, too far, too faint to detect with current telescopes. What we know comes from the comets that fall inward, their orbits betraying their origins. Every bright comet that appears in the night sky, with its glowing coma and streaming tail, may be a messenger from the Oort cloud, a visitor from the frozen shell above and below us. The turning point of the Oort cloud is that it marks the boundary of the Sun's dominance. Within the Oort cloud, the Sun's gravity is still strong enough to hold objects in orbit, though only barely. Beyond the Oort cloud, the influence of other stars becomes significant. A passing star can perturb the orbits of Oort cloud objects, sending some inward and others outward, some into the inner solar system and others into interstellar space. Above and below, the Oort cloud sits at this threshold, part of our system yet vulnerable to the galaxy. The tidal forces of the Milky Way also affect the Oort cloud. The galaxy's gravitational field, though weak at this distance, can slowly stretch and compress the cloud, stirring its contents. Over millions of years, these tidal forces can send comets cascading inward, creating showers of comets in the inner solar system. Above and below, the Oort cloud is not static but dynamic, constantly perturbed by the larger galactic environment. The turning point of the Oort cloud is also a turning point in scale. Inside the Oort cloud, we are clearly within the solar system, even if the distances are vast. Outside the Oort cloud, we are in the realm of the stars, where the Sun is just one light among many. Above and below, the Oort cloud is the last shell, the final boundary before interstellar space truly begins. The number of objects in the Oort cloud is estimated to be in the trillions, ranging from tiny icy fragments to bodies tens of kilometers across. They are spread over such an immense volume that the average distance between them is vast, but the total population is enormous, a vast reservoir of frozen material waiting for the rare nudge that sends one inward. Above and below, the Oort cloud is one of the largest structures associated with the solar system, not in mass, but in extent. The Oort cloud also connects us to other star systems. Just as our Sun has a cloud of comets, other stars likely have similar structures. Some of those comets may be ejected, becoming interstellar wanderers. In turn, some of our Oort cloud objects may one day be ejected, drifting into the galaxy. Above and below, the Oort cloud is a bridge, linking our solar system to the larger population of stellar systems through the exchange of icy bodies. The turning point of the Oort cloud is both an ending and a beginning. It is the end of the solar system, in one sense, the farthest reach of the sun's gravitational hold. But it is also the beginning of interstellar space, the threshold beyond which the galaxy takes over. Above and below, the Oort cloud marks this transition, a frozen shell that wraps us in the remnants of our past and connects us to the future of exploration. It is the turning point, the boundary, the edge of home, within the vast sphere of the Oort cloud. Trillions of icy bodies drift in silence. They are comets, frozen remnants from the birth of the solar system, waiting in the deep cold far beyond the warmth of the sun. For most of their existence, these comets are invisible, dormant, untouched by time. They orbit the sun so slowly that a single circuit can take millions of years. Above and below, they wait, and their waiting is the consequence of the solar system's violent youth, when gravity scattered countless bodies into the outer darkness. A comet in the Oort cloud is a simple thing, a mixture of ice and rock, dust and frozen gases, perhaps a few kilometers across, perhaps smaller. It formed in the early days when the solar system was a disk of gas and dust swirling around the young sun. As the planets grew, their gravity stirred the smaller bodies, flinging some inward, others outward. Those thrown outward, if they travelled far enough but not too far, settled into the Oort cloud. There they have remained, almost unchanged, for 4.5 billion years. Above and below, these frozen worlds hold within them the chemistry of the early solar system, preserved like insects in amber. The consequence of their existence is that they serve as time capsules. Unlike planets, which melted and differentiated, reforming their interiors, comets stayed cold and simple. The ices they contained, water ice, carbon dioxide ice, methane ice, are the same materials that once filled the protoplanetary disk. The dust grains within them are ancient, perhaps older than the solar system itself, survivors from the interstellar cloud that collapsed to form the sun. Above and below, the Oort cloud is a library of the past, each comet a frozen page waiting to be read. But comets do not remain in the Oort cloud forever. The consequence of their position, so far from the sun yet still within its gravitational reach, is vulnerability. Passing stars, wandering through the galaxy, can approach close enough to disturb the delicate orbits. A star passing within a few light years can alter the paths of Oort cloud objects, nudging some inward, sending others outward into interstellar space. The galaxy itself, with its slow tidal forces, can stretch and compress the cloud, stirring its contents like a spoon in a cup. Above and below, the comets wait, but their waiting is not eternal. When a comet is nudged inward, its journey transforms. For millions of years, it may have drifted in the cold darkness, reflecting no light, invisible to any observer. But as it falls toward the sun, crossing the orbits of the outer planets, it begins to warm. The sun's radiation, weak at first but growing stronger, starts to sublimate the ices. Gas streams away from the nucleus, carrying dust with it. A coma forms, a glowing cloud of gas and dust surrounding the tiny solid core. The solar wind pushes this material into a tail, stretching away from the sun, always pointing outward. The comet, once invisible, becomes a beacon, announcing its arrival. The consequence of this transformation is beauty. Comets are among the most striking sights in the night sky. Their tails can stretch for millions of kilometers, glowing softly in reflected sunlight and in the fluorescence of ionized gas. They move slowly against the stars, visible for weeks or months as they swing around the sun and head back out into the darkness. Ancient peoples saw them as omens, signs of change. Modern observers see them as visitors, messengers from the distant shell that surrounds us. Above and below, the Oort cloud sends these travellers inward, each one a consequence of its long wait. But the consequence of each comet's journey is also its destruction. Each pass near the sun strips away material. The ices sublimate, the dust is blown away, and the nucleus shrinks. After many passages, the comet may be reduced to a rocky core, its volatile materials exhausted. Some comets break apart entirely, fragmenting under the stress of heating, rotation. Others are flung out of the solar system by gravitational encounters with planets, lost to interstellar space. The consequence of falling inward is impermanence. The comets that light up our skies are dying, spending their substance in a brief display before fading forever. The consequence for Earth is profound. Comets are thought to have delivered much of our planet's water. In the early days, when Earth was still cooling, comets from the outer solar system rained down, bringing ice that eventually became oceans. They may also have delivered organic molecules, the building blocks of life. If so, then the consequence of comets waiting in the Oort cloud is not just astronomical but biological. Life on Earth may owe its existence to these frozen visitors. Above and below, the Oort cloud holds within it the seeds of habitability. The waiting comets also pose a consequence of risk. A large comet, disturbed from the Oort cloud, could fall inward on a collision course with Earth. Such impacts are rare, spaced by millions of years, but they are not impossible. The consequences of such an impact would be catastrophic, capable of causing mass extinctions. The dinosaurs may have been wiped out by an asteroid, but comets are equally dangerous. Above and below, the Oort cloud contains both the gifts of water and the threats of destruction, two sides of the same consequence. The consequence of the Oort cloud's existence also extends to other star systems. Just as our Sun has a cloud of comets, other stars likely do as well. When two stars pass near each other, their Oort clouds might overlap, exchanging comets. Some of our comets may have originated around other stars, captured long ago. Some of theirs may now orbit our Sun. Above and below, the Oort cloud connects us to the larger galactic population of comets, a vast reservoir spread across the galaxy, shared and exchanged over billions of years. The consequence of studying comets is knowledge. Missions like Rosetta, which orbited and landed on a comet, and Stardust, which collected samples from a comet's coma, have revealed their structure in detail. These missions confirmed that comets are ancient, that they contain organic molecules, that they are porous and fragile. Each discovery about comets is a discovery about the Oort cloud, even though the cloud itself is too distant to visit. Above and below, the comets that fall inward are our only direct link to the frozen shell that surrounds us. And so, the consequence of the Oort cloud is manifold. It is a reservoir of ancient material, a source of visitors, a threat and a gift, a connection to other stars. The comets within it wait in silence, drifting through the cold, until gravity nudges them onto paths that bring them into the light. Above and below, the waiting continues, patient and endless. The consequence of their existence is written in every comet that graces our skies, every icy messenger from the deep, every frozen reminder of the solar system's beginning. The Oort cloud may be filled with trillions of comets that belong to our solar system, but it is not the only source of icy travellers. Occasionally, something arrives that does not belong. An object that formed around another star was ejected and has been wandering the galaxy ever since. These are interstellar visitors, and their arrival has a profound impact on our understanding of the universe. They remind us that the solar system is not isolated, that the galaxy is filled with wanderers, and that above and below, the boundaries between star systems are permeable. The first confirmed interstellar visitor was detected in 2017. It was given the name ʻOumuamua, a Hawaiian word meaning scout or messenger arriving first. It was discovered by the Pan-STARRS telescope in Hawaii, moving through the inner solar system at a speed too high to be bound by the sun's gravity. Its trajectory showed that it had come from interstellar space, passed near the sun, and was heading back out, never to return. Above and below, it cut across the ecliptic at a steep angle, a stranger passing through. ʻOumuamua was strange in many ways. Its shape appeared to be elongated, perhaps 10 times longer than it was wide, like a cigar or a needle. It did not develop a coma or tail, suggesting it was not outgassing like a typical comet. Yet its motion showed a slight acceleration, a push that could not be explained by gravity alone. This led to speculation about its nature. Was it a comet with unusual composition? An asteroid? Something more exotic? The impact of Oumuamua was not physical. It did not collide with anything, but intellectual, forcing astronomers to reconsider what interstellar objects might look like. 2 years later, in 2019, another interstellar visitor was discovered. This one was named 2I, Borisov, after the amateur astronomer who first spotted it. Unlike Oumuamua, Borisov behaved like a comet. It had a coma, a tail, and showed clear signs of outgassing. Observations revealed that its composition was similar to solar system comets, with water, carbon monoxide, and other volatile ices. Above and below, Borisov offered a glimpse of a comet from another star, confirming that the processes that form comets are similar throughout the galaxy. The impact of these discoveries is the realization that interstellar objects are not rare. Calculations suggest that the galaxy is filled with them, wanderers ejected from their home systems, drifting through the void. Some estimates suggest that at any given time, there may be several interstellar objects passing through the inner solar system, most too faint to detect. Above and below, these visitors arrive from all directions, cutting across the plane of the solar system, tracing paths that originate in distant star systems. The impact on astronomy has been significant. Before Oumuamua, interstellar objects were theoretical, predicted, but not observed. Now, they are real, detectable, and part of the data. Telescopes are being designed with the capability to spot more of them, to track their paths, to study their composition. Each interstellar visitor is a free sample from another planetary system, a chance to learn about conditions around other stars without sending a spacecraft. Above and below, these visitors are opportunities, windows into the diversity of the galaxy. The impact on our understanding of the Oort cloud is also important. If other stars have clouds of comets, and if those clouds can be disrupted, then the galaxy must be filled with ejected comets, wandering between stars. Some of these may eventually be captured by other stars, including our Sun. This means that some of the objects in our Oort cloud may not have originated here. They may be immigrants, captured long ago from passing systems. Above and below, the Oort cloud may be a mixture of native and foreign bodies, a reminder that the boundaries of star systems are not absolute. The impact of interstellar visitors also raises questions about panspermia, the idea that life could spread between star systems. If comets carry organic molecules, and if comets can travel between stars, then the building blocks of life might be shared across the galaxy. An interstellar comet falling into a young planetary system could deliver water and organics, seeding it with the ingredients for life. Above and below, these visitors might be more than just curiosity. They might be carriers of chemistry that connects all star systems. The impact on future missions is also being felt. Proposals have been made to send spacecraft to intercept interstellar visitors, to study them up close, to collect samples. The challenge is that these objects move fast and their arrivals are unpredictable. Missions would need to be designed for rapid response, ready to launch within weeks or months of a detection. Above and below, the next interstellar visitor could arrive at any time, and humanity is preparing to meet it. The impact of these visitors is also philosophical. They remind us that the solar system is not a closed box. It is part of a larger system, the galaxy, where objects move between stars, where boundaries are fluid, where connections exist even across vast distances. Above and below, the interstellar visitors are proof that isolation is an illusion. We are connected to other star systems, not by direct contact, but by the slow exchange of wanderers over billions of years. The impact is also one of wonder. To see an object that formed around another star, that travelled for millions of years through the darkness, that passed briefly through our neighbourhood, is to feel the scale of the galaxy. Above and below, these visitors are reminders that the universe is vast, that it is filled with systems like ours, and that even in the emptiness of space, things are always moving, always travelling, always arriving. And so, the impact of interstellar visitors is both practical and profound. They give us data, they challenge our theories, they open new avenues of exploration, but they also give us perspective. Above and below, the galaxy is alive with motion, and the boundaries we draw around the solar system are only conventions. The visitors remind us that we are part of a larger whole, connected by the wanderers that drift through the darkness, arriving from the deep, passing through, and continuing onward into the infinite. In the midst of all this vastness, the structures stretching for light years above and below, the comets waiting in frozen shells, the dark matter wrapping the galaxy, the interstellar visitors arriving from distant stars, there is something easy to forget. There is us. Humanity, living on a small planet, grounded by gravity, looking up at the night sky and asking questions. The human element in the story of what lies above and below is not about our size, which is tiny, but about our perspective, which is extraordinary. We stand on Earth, a world 8,000 miles across, orbiting a star 93 million miles away. The solar system extends billions of miles, the Oort cloud trillions. The galaxy stretches 100,000 light years. The distances are so vast that they lose meaning, numbers on a page rather than things we can feel. And yet, we can imagine them, we can measure them, we can map them. The human element is this ability to comprehend scale, even when the scale dwarfs us beyond measure. Above and below are concepts we understand instinctively on Earth. We walk on the ground, we look at the sky. Gravity pulls us down, and up is the opposite of down. These are truths written into our bodies, into the way we move and see. But when we extend these concepts into space, we are performing an act of imagination. We are taking the familiar and stretching it across distances where it no longer applies literally. The human element is this, translation, this willingness to use what we know to explore what we do not. The perspective from Earth is both limiting and liberating. Limiting because we can only see a small part of the sky at once, because dust and light pollution obscure the stars, because our eyes detect only a narrow band of wavelengths. But liberating because we have built tools to extend our senses. Telescopes that see infrared and ultraviolet, radio dishes that detect faint emissions, space observatories that peer through the atmosphere. Above and below, we have found ways to see farther than our biology allows, to map the invisible, to trace the hidden. The human element also includes the emotional response to these discoveries. When we learn that the heliosphere protects us, there is comfort. When we discover that dark matter dominates the galaxy, there is awe. When we see a comet streak across the sky, there is beauty. When we realize that interstellar visitors arrive from other stars, there is wonder. These emotions are not separate from the science. They are part of it. Part of why we explore. part of what drives us to ask what lies above and below. We are also shaped by the knowledge of scale. To know that we live inside a bubble, surrounded by a cloud of comets, wrapped in a halo of dark matter, changes how we see ourselves. We are not at the center of the universe. We are not the largest or the most significant, but we are observers, witnesses, thinkers. The human element is this consciousness, this ability to step outside ourselves and see where we fit in the vastness. Above and below, the structures are indifferent to us, but we are not indifferent to them. The perspective also includes humility. The more we learn about what lies above and below, the more we realize how much we do not know. Dark matter is a mystery. The Oort cloud has never been seen directly. Interstellar visitors arrive unexpectedly. The galaxy is full of structures we are only beginning to map. The human element is the willingness to admit ignorance, to say we do not know, and to keep searching anyway. Above and below, the unknown is vast, but it is also an invitation. There is also resilience in the human element. We live on a planet vulnerable to cosmic rays, to comets, to the forces of the galaxy. Yet we endure. The heliosphere shields us. The magnetic field of Earth deflects particles. The atmosphere absorbs radiation. We exist in a narrow band of conditions, a fragile balance, yet we thrive. Above and below, the universe is not designed for us, but we have found our place within it, carving out a home in the midst of vastness. The human element is also curiosity. We did not need to ask what lies above and below the solar system. We could have looked only at the ground, focused only on survival. But we looked up. We wondered. We built instruments and sent spacecraft. We drew maps and wrote theories. Above and below, the structures we discovered were always there, but it took human curiosity to reveal them. The act of asking is itself a human contribution to the cosmos. There is connection as well. When we study the galaxy, we learn about the forces that shaped Earth. The heavy elements in our bodies were forged in stars. The water in the oceans may have arrived on comets. The magnetic field that protects us is generated by the same processes that shape other planets. Above and below, we are made of the universe, part of it, not separate from it. The human element is the recognition of this connection, the understanding that we are both observers and participants. The perspective from Earth is also a vantage point. From here, we can see the galaxy edge on, the band of the Milky Way stretching across the sky. From here, we can measure the positions of stars, the motions of gas, the bending of light. From here, we can ask what lies above and below and begin to answer. Above and below, Earth is the place from which we look, and that makes it central in a different way. Not the center of the universe, but the center of our perspective. And so, the human element in the story of what lies above and below is this. We are small, but we are aware. We are brief, but we are curious. We are fragile, but we endure. We stand on a planet, looking out into the vastness, and we see structures that dwarf us, but we also see them, and in seeing, we connect. Above and below, the universe is vast, but we are here, and that matters, not to the universe, but to us, and that is enough. When we imagine the Milky Way, we often picture it as a perfect spiral, a flat disk of stars rotating smoothly around the galactic center. This image is tidy, symmetrical, easy to hold in the mind, but the reality is messier. The Milky Way is not flat. Its disk is warped, bent upward on one side and downward on the other, like a record left too long in the sun. This warping is the opposition to the idea of a simple, planar galaxy. It shows that the Milky Way is dynamic, shaped by forces both internal and external. Above and below, the warp defines how the disk curves, how it rises and falls in a slow wave. The discovery of the warp came from observations of hydrogen gas in the outer regions of the galaxy. Radio telescopes, mapping the distribution of neutral hydrogen, noticed that the gas did not lie in a single plane. Instead, it tilted, rising above the plane on one side and dipping below it on the other. Later surveys of stars confirmed that the stellar disk is also warped, though less dramatically than the gas. The overall picture is of a disk bent into a shallow shape, curving gently above and below the central plane. The causes of the warp are still debated, but several factors are likely at work. One possibility is the gravitational influence of nearby satellite galaxies, such as the Large and Small Magellanic Clouds. These companions orbit the Milky Way, and their tidal forces can pull on the disk, creating ripples and bends. The distribution of dark matter in the halo. If the dark matter halo is not perfectly spherical, its uneven gravity could twist the disk. Interactions with past mergers, streams of stars, and even the motions of gas in the outer regions all contribute. Above and below, the warp is the result of these combined forces, a dynamic response to the galaxy's environment. The warp is not unique to the Milky Way. Many spiral galaxies show warped disks when seen edge-on. Photographs of galaxies like NGC 4013 or ESO 510G 13 reveal bent shapes, their outer regions curving gracefully above and below the central plane. This suggests that warps are common, perhaps an inevitable feature of spiral galaxies. The opposition to flatness is universal. Above and below, galaxies curve, shaped by their halos, their companions, and their histories. The scale of the warp is enormous. The Milky Way's disk is about 100,000 light-years across, and the warp raises and lowers the outer edges by several thousand light-years. Imagine a vast ocean frozen mid-wave, with crests and troughs spanning tens of thousands of light-years. That is the scale of the galactic warp. Above and below, the disk arches and dips, carrying stars and gas along its bent surface. The bending creates regions where material flows differently, where gravity pulls in directions slightly off from the central plane. This can influence star formation, creating asymmetries in the distribution of young stars. It can also affect how gas settles, shaping the spiral arms. Above and below, the warp is not just a geometric feature, but an active part of the galaxy's dynamics, influencing how matter moves and where new stars are born. The solar system's relationship to the warp is complex. The ecliptic plane, defined by Earth's orbit, is tilted by about 60 degrees relative to the galactic plane. This means that our local definition of above and below does not align perfectly with the galaxies. Add the warp to this, and the geometry becomes even more layered. The galactic plane itself is not flat, so the direction we call above or below in galactic terms depends on where we are in the disk. Above and below, the warp adds curvature to the map we use to navigate the galaxy. The warp also shows that the galaxy is not static. It is constantly shifting, responding to the forces acting on it. Over billions of years, the warp may grow, shrink, or change its shape depending on how the Milky Way interacts with its companions and its dark matter halo. The bent shape we see today is only a snapshot, a moment in the galaxy's long evolution. Above and below, the warp is a reminder that galaxies are living systems, always in motion, always changing. Some studies suggest that the warp may not be static but oscillating, like a wave passing through the disk. This could be driven by interactions with satellite galaxies or by the uneven pull of dark matter. If true, then the warp is not a fixed bend but a moving wave, slowly shifting over millions of years. Above and below, the disk rises and falls in a rhythm too slow for us to perceive, but real nonetheless. The opposition of the warp is also philosophical. It challenges the assumption that structure must be orderly, that galaxies must be simple. The Milky Way is not a neat spiral drawn on a flat plane. It is bent, asymmetrical, shaped by countless forces. Above and below, the warp reminds us that the universe is messy, that structure is not rigid. The opposition to flatness is a celebration of complexity. For astronomers, mapping the warp requires careful observation. Radio telescopes trace the hydrogen gas, while surveys of stars add detail. Infrared observations penetrate the dust, showing the distribution of stars more clearly. Each method contributes to a picture of the warp, confirming its presence and refining its shape. Above and below, the warp is being mapped, measured, understood. And so, the galactic warp is the opposition to the simple picture of a flat disk. It shows that the Milky Way is bent, shaped by gravity, by companions, by history. Above and below, the disk curves, rising and falling in a slow, majestic wave. The warp is dynamic, complex, and beautiful. It is one more layer in the story of what lies above and below, a reminder that even galaxies are shaped by forces we are only beginning to understand. When we think of what lies above and below the solar system, we often picture large structures, the Heliosphere, the Oort cloud, the halo of the galaxy. But between these grand features, woven through the space like threads in a tapestry, are smaller, subtler structures. These are the hidden filaments, streams of stars, ribbons of gas, and lines of magnetic force that fill the space above and below. They are not always visible, not always obvious, but they are essential. The awakening is the realization that the galaxy is not made of a few large pieces, but of countless threads, all connected, all part of a larger whole. Stellar streams are one form of these hidden filaments. As we have discussed, they are the remnants of smaller galaxies torn apart by the Milky Way's gravity. But there are also streams formed from disrupted star clusters, from gas stripped away by tidal forces, from material ejected by supernova. Above and below, these streams arc through the halo, faint trails of stars and gas that mark the history of the galaxy's growth. Each stream is a thread, and together they form a web of connections, linking the past to the present. Filaments of gas are another part of this hidden structure. The interstellar medium is not uniform. It is clumpy, textured, filled with regions of higher and lower density. Some of these regions are organized into filaments, long, thin structures that stretch for light years. These filaments can be cold, dense clouds, where stars are born, or they can be hot, ionized gas flowing through the galaxy. Above and below, the filaments connect clouds, feed star-forming regions, and channel matter through the disk and halo. Magnetic fields also form filaments, though they are invisible to the eye. The galaxy is threaded with magnetic field lines, shaped by the rotation of the disk, by the motions of gas, by the influence of stars and supernova. These fields guide the motion of charged particles, shaping the flow of cosmic rays and the structure of the interstellar medium. When observed in radio wavelengths, the magnetic fields reveal themselves as long, thin strands of emission, filaments that stretch above and below the galactic plane. The awakening is seeing that even the invisible has structure, that the galaxy is woven together by fields we cannot touch but can measure. High-velocity clouds are another type of hidden filament. These are large concentrations of gas moving at speeds different from the rotation of the disk. Some are falling into the Milky Way from intergalactic space, while others are material blown out of the disk by supernova and now raining back down. Above and below, these clouds drift, arcing through the halo, connecting the galaxy to its surroundings. They are streams of matter, feeding the galaxy, cycling material through the system, keeping the process of star formation alive. The Magellanic Stream is one of the most dramatic examples of a hidden filament. It is a long ribbon of gas stretching across the southern sky, trailing behind the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This stream was pulled out by tidal forces as the dwarfs interacted with our galaxy, leaving behind a filament of hydrogen that spans more than half the sky. Though invisible to the naked eye, it is mapped clearly in radio observations. Above and below, the Magellanic Stream is a reminder that galaxies are connected by threads of matter, that the boundaries between them are blurred. The awakening also involves recognizing that filaments are not just remnants but active structures. They channel matter, guide flows of gas, feed star-forming regions. In some cases, filaments may be the highways along which material moves through the galaxy. Above and below, these threads are not static but dynamic, carrying matter and energy, shaping the environment. The cosmic web, the large-scale structure of the universe, is also made of filaments. On the grandest scales, galaxies and galaxy clusters are arranged along thin strands of dark matter and gas, connected by these filaments. The Milky Way is part of this web, linked to other galaxies by invisible threads. Above and below, the filaments of the cosmic web extend, connecting our galaxy to the larger universe. The awakening is seeing that structure exists at every scale, from the smallest streams of stars to the largest cosmic threads. Hidden filaments also connect to the idea of the galactic fountain. Supernova and stellar winds blow hot gas out of the disk, pushing it upward into the halo. This gas cools, condenses into clouds, and eventually falls back down, forming filaments of cooler material. Above and below, this cycle creates a flow, a circulation of matter through the galaxy. The filaments are the channels through which this matter moves, connecting the disk to the halo, the past to the future. The awakening is also about tools. Many of these filaments are invisible in optical light. They require radio telescopes to map the gas, infrared instruments to see through dust, ultraviolet detectors to trace ionized material. The awakening is not just about what lies above and below, but about how we see it, about the technology that reveals the hidden. Above and below, the filaments are always there, but they become visible only when we build the right instruments. The hidden filaments also tell us about the interconnectedness of the galaxy. Nothing is isolated. Stars are born from gas, die in explosions, and return material to the interstellar medium. That material forms new clouds, new stars, new filaments. Above and below, the threads connect everything, weaving the galaxy into a single system. The awakening is recognizing this web, seeing the connections, understanding that the galaxy is not a collection of separate pieces, but a unified whole. And so, the hidden filaments above and below the solar system are streams of stars, ribbons of gas, lines of magnetic force, all woven together into a tapestry. The awakening is the realization that the galaxy is full of threads, that structure exists at every scale, that nothing is truly separate. Above and below, the filaments stretch, invisible but essential, connecting the past to the present, the disk to the halo, the Milky Way to the cosmos. The awakening is seeing the threads and understanding the weave. After following the layers above and below the solar system, after tracing the heliosphere, Oort cloud, the halo, the streams, the dark matter, the warp, and the filaments, we arrive at a revelation. A truth that has been present all along, but becomes clear only now. Above and below are not absolute. They are relative. They are choices we make, frameworks we create, maps we draw to navigate a universe that has no natural up or down. The revelation is that direction in space is a human construct, useful but not universal. On Earth, above and below are obvious. Gravity pulls us toward the center of the planet, defining down. Up is the opposite, away from the ground, toward the sky. These directions are written into our bodies, into the way we stand, walk, and see. We cannot escape them. They feel like truths, as solid as the ground beneath our feet. But in space, there is no ground. There is no single pull of gravity defining a universal down. The revelation is that we must let go of this instinct and embrace the relativity of direction. The ecliptic plane, the disk traced by. Earth's orbit is one framework. It defines above and below in solar system terms. North of the plane is above, south of the plane is below. This is useful for mapping planets, asteroids, comets, and the structure of the Oort cloud. But it is arbitrary. We could just as easily choose a different plane, define different poles, and the map would change. Above and below in this context are only meaningful because we chose them. The galactic plane is another framework. The Milky Way's disk defines a different set of directions, tilted by about 60 degrees relative to the ecliptic. The north galactic pole points toward Coma Berenices, the south toward Sculptor. These directions are useful for understanding the structure of the galaxy, the halo, the streams, the warp. But again, they are chosen. The galaxy does not come with labels. We applied them. Above and below in galactic terms are conventions, not laws. The revelation deepens when we consider that the solar system is moving. It orbits the galactic center, taking hundreds of millions of years to complete one circuit. As it moves, it bobs gently above and below the galactic plane, oscillating like a bead on a string. What is above us now was beside us millions of years ago and will be below us millions of years from now. The directions shift with time. The structures remain, but our relationship to them changes. Above and below are not fixed but dynamic, evolving with the motion of the solar system. The revelation also touches on perspective. If we could step outside the Milky Way and look back, we might choose to define above and below differently. From the Andromeda Galaxy, the orientation of the Milky Way would look different. From a galaxy in the Virgo cluster, different still. Each observer, each vantage point, would create its own map, its own definitions. Above and below are observer dependent. They are not properties of space, but properties of how we look at space. Even within our own galaxy, the relativity is clear. An observer on a planet in the galactic halo would define directions differently than we do. An observer in a globular cluster orbiting high above the disk would see the Milky Way from above, from what we call the North Galactic Pole. To them, that direction would not be above but forward, or inward, or some other term tied to their own reference. The revelation is that there is no single correct map, only maps that suit different purposes. The relativity of direction also applies to the cosmic web. On the largest scales, galaxies are arranged in filaments and clusters, but there is no universal orientation. The web has no top or bottom, no preferred axis. Each galaxy, each cluster, defines its own local directions. The Milky Way's north is not the universe's north. Above and below on cosmic scales are entirely relative, dependent on where you are and what structures you are using as reference. This revelation is not a failure of astronomy, it is a strength. By recognizing that above and below are relative, we free ourselves to use the frameworks that are most useful. We can map the solar system with the ecliptic, map the galaxy with the galactic plane, and map the cosmic web with no preferred orientation at all. Each framework serves a purpose. None is more true than the others. The revelation is that relativity is not confusion, but flexibility. The revelation also connects to the nature of space itself. Space is not like a room with a floor and a ceiling. It is a three-dimensional volume, or perhaps a four-dimensional space-time, with no preferred directions. Gravity shapes it, matter curves it, but there is no universal up or down. The directions we use are imposed by us, by our need to orient ourselves, by our desire to make sense of the vastness. Above and below are human words for a universe that does not speak our language. There is also a philosophical dimension to this revelation. If above and below are relative, then so are many other things we take for granted: center and edge, near and far, inside and outside. All of these depend on perspective, on reference frames, on the maps we draw. The universe does not organize itself for our convenience. We organize it ourselves, and that act of organization is part of what it means to explore, to understand, to wonder. Above and below are not discoveries. They are creations. The revelation is also liberating. It means that when we ask what lies above and below the solar system, we are not asking about absolute truths, but about useful descriptions. The heliosphere, the Oort cloud, the halo, the streams, the warp, the filaments, all of these structures are real, but the language we use to describe their positions is flexible. Above and below are tools, and we are free to use them however they help us see. And so, the revelation is this: above and below are relative. They are frameworks, maps, choices. They help us navigate the vastness, but they are not written into the cosmos. The universe has no preferred directions, only the ones we create. Above and below the solar system lie structures, forces, and mysteries. But the words themselves are ours, and that is enough. The revelation is that relativity is not a limitation. It is the way the universe works, and embracing it is the key to understanding. Between the grand structures, between the heliosphere and the Oort cloud, between the streams of stars and the filaments of gas, lie vast stretches of near emptiness. These are the quiet lanes, regions of space where matter is so sparse that it seems like nothing at all. They are not voids in the absolute sense, but they are the calmest, thinnest parts of the galaxy. Above and below, these lanes stretch, and in their silence, they define the scale of the cosmos as much as the bright structures do. The quiet lanes are found in the interstellar medium, the space between stars. In some regions, the gas is denser, forming clouds where stars are born. In others, the gas is thinner, spread so sparsely that encounters between atoms are rare. These thinner regions are the quiet lanes. A cubic centimetre might contain only a handful of atoms, far fewer than even the best laboratory vacuum. Above and below, the lanes are empty enough to feel like true void, though they are never completely so. The solar system is currently passing through one such region, the local bubble, a cavity carved out by ancient supernova. Within this bubble, the gas is hot but sparse, blown clear by the explosions that shaped it. The quiet lanes within the bubble offer an open view, less interference from dust and gas, clearer paths for light to travel. Above and below, the bubble surrounds us, and the lanes within it are the roads through which we see the galaxy beyond. The quiet lanes are also where interstellar visitors travel. Objects like ʻOumuamua and Borisov, ejected from their home systems, drift through these regions on journeys that span millions of years. The probability of encountering anything in the quiet lanes is tiny. The distances are vast, the densities low. An object could travel for 1 million years without coming near another star, another planet, or even a significant cloud of gas. Above and below, the lanes are highways of silence, open and empty, free of obstacles. The reflection on these lanes is one of scale. When we imagine space as empty, the quiet lanes are what we mean. They are the baseline, the default state of the galaxy. The bright structures, the stars, the clouds, the filaments are exceptions, islands of matter in a sea of near nothing. Above and below, the lanes are the majority. the background against which everything else is defined. The reflection is that most of the galaxy is quiet, sparse, and still. But even in the quiet lanes, there is subtlety. Magnetic fields thread through, weak but present. Cosmic rays pass, high-energy particles streaming from distant sources. A few atoms drift, hydrogen and helium mostly, too thin to clump but still there. Photons from distant stars cross the lanes, carrying light that has travelled for thousands or millions of years. Above and below, the lanes are not truly empty. They are filled with the faintest traces of matter and energy, enough to give them texture. The quiet lanes also play a role in observation. When astronomers look through them, they can see farther. The lack of dust and gas means less interference, less absorption, clearer signals. The galactic poles, for example, open into quiet lanes, offering windows to the distant universe. Above and below, the lanes are where we look when we want to see beyond the Milky Way, when we want to study the cosmic microwave background or distant galaxy clusters. The quiet lanes are transparent, and transparency is valuable. The reflection also touches on the nature of emptiness. In daily life, we are surrounded by matter, air, ground, objects, people. Emptiness is rare, fleeting, but in space, emptiness is the norm. The quiet lanes are a reminder of this. They show us that the universe is mostly nothing, that matter is the exception, not the rule. Above and below, the lanes stretch for light years, and within them, there is almost nothing. The reflection is that emptiness is not absence, but presence of a different kind. The quiet lanes are also places of waiting. Comets drift through them, silent and unseen. Interstellar clouds float, too diffuse to form stars. Dark matter fills the volume, shaping the lanes with invisible gravity. The lanes are not active, not dynamic, but they are patient. Above and below, they wait, holding space, defining the gaps between the bright structures. The reflection on the quiet lanes also brings calm. In a universe full of violent events, supernova, collisions, stellar winds, the lanes are peaceful. Nothing happens there. Nothing changes. They are the resting places of the galaxy, the pauses between bursts of activity. Above and below, the lanes offer silence, and silence is its own kind of answer. The reflection is that stillness is not emptiness but fulfillment, the state where motion has ceased and balance has been reached. For spacecraft travelling outward, the quiet lanes are the future. Beyond the Heliosphere, into the interstellar medium, the Voyagers are crossing these lanes now. They will continue for decades, perhaps centuries, drifting through the sparse regions, sending back data from the silence. Above and below, the lanes are where humanity's farthest explorers will spend most of their time, in the calm between the stars. The reflection on the quiet lanes is also philosophical. They remind us that the universe is not crowded. It is spacious, open, generous with room. The lanes are the canvas on which the structures are painted. Without them, there would be no contrast, no way to see the stars as bright, the clouds as dense, the streams as coherent. Above and below, the quiet lanes give meaning to the structures by being different from them. And so, the quiet lanes above and below the solar system are the stretches of near emptiness, the sparse regions where matter is thin and events are rare. They are the background, the majority, the calm. Above and below, they stretch, silent and patient, holding space, defining scale, offering transparency. The reflection is that the lanes are as essential as the structures, that emptiness is as important as fullness, that silence is as meaningful as sound. The quiet lanes are where the universe rests, and in their rest they complete the story. We have travelled far in thought, lifting our gaze above the solar system and peering down below it. We have traced the invisible bubble of the heliosphere, felt the protection of its cocoon. We have crossed into the interstellar medium, where gas and dust drift between stars. We have looked through the windows of the galactic poles, seen the ancient halo with its globular clusters and dark matter. We have followed streams of disrupted galaxies, threads of stars arcing through the void. We have imagined the Oort cloud, its frozen shell surrounding us at unimaginable distances, comets waiting in silence. We have met interstellar visitors, wanderers from other star systems passing briefly through our neighborhood. We have recognized the warp of the galaxy, the bending of the disk, the way structure is never rigid. We have awakened to the hidden filaments, the threads of gas and magnetic fields that weave the galaxy together. We have understood the revelation that above and below are relative, frameworks we choose rather than absolute truths. And we have reflected on the quiet lanes, the vast stretches of near emptiness that define the background of the cosmos. Now it is time to return home, to step back from the vastness and remember where we are. Home is Earth, a small planet orbiting a middle-aged star 8 light minutes from the sun. It is a world of oceans and continents, atmosphere and life. It is where you are now, perhaps lying in bed, perhaps sitting in a chair, perhaps looking out a window at the night sky. Home is the place from which we ask the questions, the vantage point from which we explore. Above and below, the structures we have traced are real, but they are distant. Home is here, and here is where the journey begins and ends. Returning home does not mean forgetting the vastness. It means carrying it with us, holding it in perspective. When you look up at the night sky, you can remember that above you, beyond the atmosphere, beyond the heliosphere, lies the interstellar medium. Beyond that, the Oort cloud, a sphere of comets wrapping the solar system. Beyond that, the halo of the galaxy, ancient stars and dark matter. Beyond that, the cosmic web, galaxies linked by filaments stretching across the universe. Above you, all of this exists, layered, nested, extending farther than light can travel in a human lifetime. And below you, the same. Structures mirror back. The heliosphere extends downward as well as upward. The Oort cloud wraps beneath as well as above. The galactic halo stretches in all directions. The quiet lanes, the streams, the warp, the filaments, all of them are present below as they are above. The symmetry is beautiful. The universe does not favour one direction over another. Above and below are equal, balanced, part of the same whole. Returning home also means recognising our place. We are small, yes. A planet in a solar system in a galaxy in a universe. The scales dwarf us. But we are also observers, thinkers, explorers. We are the ones who ask what lies above and below. We are the ones who build telescopes and send spacecraft. We are the ones who draw maps and tell stories. Returning home is not a retreat into insignificance. It is an acknowledgement of connection. We are part of the cosmos, made of its atoms, shaped by its forces, alive within its structures. There is also comfort in returning home. The vastness can feel overwhelming. The distances, the scales, the mysteries, they can make us feel lost. But home is a place we know. The ground beneath our feet, the air we breathe, the familiar rhythms of day and night, of seasons, of life. Returning home is returning to the scale where we live, where we can act, where we matter. Above and below, the structures are vast, but here, at home, we are present. Returning home also brings perspective. The cosmic rays that stream through the galaxy, the comets that fall from the Oort cloud, the dark matter that fills the halo, all of these affect Earth. We are not isolated. The heliosphere shields us. The magnetic field deflects particles. The atmosphere absorbs radiation. Home is protected, but it is not separate. We live within the galaxy, not apart from it. Returning home is remembering this connection, this embeddedness in the larger whole. The reflection on returning home is also about gratitude. To exist at all is extraordinary. To exist on a planet with oceans and life, orbiting a stable star, protected by a heliosphere and a magnetic field, is even more so. The structures above and below are beautiful, but they are also indifferent. They do not care whether we exist. Home is the place where we do exist, where conditions are just right, where the balance holds. Returning home is being grateful for this narrow window of possibility. And so, as we close this journey, we return to Earth. We return to the place from which we look, the point in space where we ask questions and seek answers. Above us, the heliosphere, the Oort cloud, the halo, the streams, the warp, the filaments, the quiet lanes. Below us, the same structures, mirroring, balancing, completing the picture. And here, at home, we stand between, observers of the vastness, participants in the cosmos, alive in the luminous middle. Thank you for journeying with me tonight. If this slow exploration of what lies above and below has brought you calm or curiosity, or simply a gentle way to rest, I am glad. You can return to this space whenever you need, whenever you want to step back from the noise and look up at the stars. Above and below, the universe is always there, waiting, holding you in its vastness. And here, you are safe, right at home, between it all. Good night.